The binomial theorem. In general, what this is going to reference is taking a binomial like a plus b and then raising it to different powers like the second power, the third power, the fourth, the fifth, the sixth, and so on. And how we might be able to figure out what that is a little bit faster. So for the beginning part, what I want to do here is demonstrate the tedious nature of actually doing this, taking a plus b and squaring it, taking a plus b and cubing it. Okay, a plus b squared is not really a lengthy problem, but you're going to notice that when we change it to a cubed, it does become more lengthy because you literally have to build off of your last answer. So if we were going to go to a plus b to the fifth power, you can imagine how lengthy this actually will become. Okay, so let's start with this guy here, a plus b squared. All right, now the first point to make, and everybody should already know this, you cannot distribute an exponent across addition. It does not work. You can distribute it across multiplication or even division if you had a fraction, but you cannot distribute across addition or subtraction. So to figure out what this is, you literally need to expand it out and think about all the distribution that occurs between the a's and the b's. Okay, so we're going to multiply a times a, which gives you a squared, then a times b, which gives you ab, then b times a, which is the same thing as a times b, so I'll just write it as ab. And last, you're going to have b times b, which is b squared. The middle terms will group together, and you're going to get a squared plus 2ab plus b squared. Okay, that is the work required to figure out what a plus b squared would be in what we call standard form. Looks like that. A plus b cubed would mean you've got 3 of these. You have 3 of those to do. The good news is we've already figured out what the product of 2 of them is. Okay, so this could just actually be a plus b times a squared plus 2ab plus b squared. But if we had started with this, you would have needed to figure out that part to get that part first. All right, so next we're going to distribute the a to all 3 of those terms, which is going to give us a cubed plus 2a squared b plus ab squared. And then we're going to multiply b times each of those terms, which is going to start with a squared b. Of course, a squared b sort of looks like this one here, so I'm going to write it underneath it, a squared b. And b times 2ab is going to create an ab squared, which looks like that. So I'm going to go ahead and write down 2ab squared. Then b times b squared will give us a b cubed. And by setting up that way, it makes it easier to group like terms. We get a cubed plus 3a squared b plus 3ab squared plus b cubed. So you can imagine what it would look like to do a plus b to the 4th power. We would need to take this result and multiply that by an a plus b. And in just a bit, we're going to do that to make the point that this is incredibly tedious to do. Overall, the goal here is to figure out how we can take a binomial and raise it to a power without having to go through all the preceding terms. And the trick to doing this is to use something called Pascal's triangle, which is this over here. Pascal's triangle is created by taking the sum of 2 adjacent elements in the preceding row. For example, if I take 1 plus 2, these are adjacent elements, they create the element that's below them and sitting in between. So 1 plus 2 is 3. Same thing here, 2 plus 1 is going to give me 3. And down here, I'm going to get 1 plus 3 gives me 4, 3 plus 3 gives me 6, 3 plus 1 gives me 4. And you can continue to do this beyond that point. So sitting right here would be a 10, and that would also be a 10 and a 5 and a 5, and you are going to have 1s on the edges there. The whole triangle begins with the number 1. We start with that element here in the top row. Next to that, we don't have any elements, so we pretend that those are zeros. And if you took 1 plus 0, you would get 1. And if you take 0 plus 1, you get 1, and that produces your second row. We then imagine that we also have zeros on the outside here. So 1 plus 0 gives you 1. You then have 1 plus 0 gives you 1, and so on. So you are going to have 1s all along the edges. Okay, then the numbers in the inside will become something different as we're adding those adjacent terms. All right, so here's a really neat observation about Pascal's triangle. The coefficients of a plus b to the powers of 1, 2, and 3 can actually be seen in the second, third, and fourth rows. Okay, so let's just look at a plus b. The coefficients of a and b are both 1s. You have a 1a and you have a 1b, which could match those two numbers here, 1 and 1. Okay, when we took a plus b and squared it, we got a squared plus 2ab plus b squared. And if you look at the coefficients, you have a 1, you have a 2, and you have a 1, which are here, 1, 2, and 1. And then to the third power, we had a cubed plus 3ab squared. Actually, sorry, that was a squared b plus 3ab squared plus b cubed. And the coefficients here are going to be 1, 3, 3, 1, which matches this. So as a prediction, if we were to figure out, and we are going to in a moment here, a plus b to the fourth power, we should get the coefficients 1, 4, 6, 4, 1. So let's check that out. I'm going to start with taking a plus b and multiplying it by a plus b to the third power, which will save some time here. Okay, let's double check everything looks good. It does. All right, we'll distribute a to all the terms. Just give us a to the fourth plus 3, a cubed b squared, nope, a squared b. The only thing that changes with the a distributing is that all the a's are going to go up by one exponent. So we have 3a squared b squared. And at the end here, we're going to have plus a b cubed. Okay, and then when you distribute the b, that will just increase all the terms by power of b. The first term that we're going to get is a b times a cubed, which could be written as a cubed b, matching this. B times the next is going to give you 3a squared b cubed. Nope, that'll be squared. I got to keep track of all these. All right, so b multiplied here, you get 3a squared, but it'll be b squared. We then get 3ab cubed. And at the end, we get b to the fourth. And if we add everything together, we're going to get a to the fourth plus, this will be 4 a cubed b plus 6 a squared b squared plus 4 ab cubed plus b to the fourth. And if you check your coefficients, we got 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. All right, so the only thing that we haven't figured out yet is what is true about the exponents. We figured out the coefficients, like if I raise this to the fifth power, I can be guaranteed the coefficients will be a 1, a 5, a 10, 10, 5, and a 1. But what about the exponents? Because that's, half of the problem too. All right, so Pascal's triangle can be used to identify the coefficients when we take a binomial and raise it to a power. Notice that the top row, which we hadn't used beforehand, notice that that top row is just equal to 1. And if you take a plus b, or you take anything and you raise it to the first power, the response back that you get is a 1. Okay, so I wanted to include here that the top row does actually apply to something, and it applies to a power of 0. This would be the power of 1, the power of 2, 3, 4, and 5. You get those powers. In addition to the coefficients, we still got to figure out what powers a and b will be raised to within the terms. Okay, so here's an observation. Notice that the first term of the expansion of this is always going to be 1 times a to the n power, b to the 0 power. In other words, you don't have any b's. But that first term You don't even have to write the 1. That first term is just going to be a to the power. For example, when we did a plus b to the third power, it started with a to the third power. It started with that term. And for each successive term, the exponent of a decreased by 1. All right, so remember back that a plus b to the third power looks like this. It begins with a cubed. Then after that, the a's decrease by 1. You get a squared, you get an a, and then you don't have any a's. The b's do the exact opposite. You don't have any b's at the end. It's almost like as you lose an a, when it drops to a squared, you gain a b. And as you lose another a, you gain another b. And once you're all out of a's, you're completely b, you've got b cubed. But the pattern is the opposite. You start with b cubed at the very end, and it decreases this direction until you don't have any b's. All right, for example 1, we're going to expand out x plus y to the 6th power. From Pascal's triangle, we can go ahead and figure out what the coefficients are. Of course, this picture right here only goes to the 5th power. That would be the 0, the 1st, 2nd, 3rd, 4th, and then 5th power. So for the 6th power, we need one more row, which would be a 1, 6, 15, 20, 15, 6, and 1. So we have 7 terms here. Okay, what I'm going to do is space those out. I'm going to attempt to not space them out too much because I might actually run out of room here. Don't need the plus yet. 6, and you got a 1. Let's move that one over just a little bit. It's about there. Okay, now as far as the x's and y's, at the very beginning, you're going to get x to the 6th power. After that, it's going to drop down to x to the 5th, but you're going to gain a y. You get a y. Then drops to x to the 4th, and you get y squared. Drops to x cubed, you also get y cubed. And as we do this, also notice that the sum of the exponents is consistently 6. You've got 6, you've got 5 plus 1, you've got 4 plus 2, 3 plus 3, 2 plus 4. We got 1 plus 5, and at the end, we got completely y's, y to the 6th power. Okay, from here, we're just going to clean things up. You don't actually have to have that 1. You can just call it x to the 6th power. Everything here is just going to be addition. And that's it. And that's definitely better than using the process of taking x plus y and multiplying it by itself 6 times. For example 2, we're going to look at what happens when we have subtraction in our binomial. Okay, now everything's going to start out the same way with the coefficients. So if I go to Pascal's triangle and look at what would really be the 5th row, it's going to have the terms 1, 4, 6, 4, and 1. Okay, so these will be the coefficients that we have for the 4th power. The first is going to be x to the 4th. After that, we're going to get x cubed with a y. We then have x squared, y squared. Let's space these out. We then get x, y cubed, and at the end, you get y to the 4th. Okay, so how does the subtraction change things? You have to think that that subtraction is a negative attached to the y value. Whenever a negative number is raised to an even power, such as right here, the negative that it carries with it will cancel and become positive. So this will be a positive term. Same thing here. When your exponent is 4, which is even, this is going to become positive. But when you have an odd exponent, like y to the 1st power, that negative doesn't cancel out. It carries through, so you have the negative here. Same thing with that. In other words, if you have a binomial with subtraction, the signs are going to alternate as you go through. Okay, so to clean things up, we don't really need to do much. We can just take out the 1 here, take out the 1 there, and that's it. All right, for example 3, we're going to look at a more realistic example, which is x plus 2 raised to the 5th power. We tend to see that more often than 2 variables. By the way, you may notice that the sun seems to be creeping in on me here, so let's see if we can get this one done before that gets into my work here. Okay, raising to the 5th power, you're still going to use the same coefficients, which is going to be a 1, then a 5, then you got a couple of 10s, you have a 5, and you have a 1. Okay, so you have a total of 6 terms. We're going to get, might not have spaced these well here, so I'll just try and squeeze them in. We're going to get x to the 5th. You're going to get x to the 4th, but you're going to pick up a 2. Over here, you're going to have x cubed. Let's go ahead and just do all the x's. Okay, you got all those x's. The 2's are going to increase. You get 2 squared. You get 2 to the 3rd, 2 to the 4th, and 2 to the 5th. Okay, so how things change here, you actually need to take that 2, make sure that you multiply by the 5. Take this 2, square it, multiply by the 10, and so on. In addition, because this is a positive, all of these will be plus. Okay, so the first term is going to be x to the 5th. The second is going to be 5 times 2, which is 10, x to the 4th. For the third, we're going to get 4 times 10, so we get 40 x cubed. Next, we get 2 to the 3rd power, which is 8. 8 times 10 is 80. After that, we've got 2 to the 4th, which is 16. 16 times 5 is 80. And last, we've got 2 to the 5th, which is 32. And that's it.
Later, blah.